You know, from the very glasses that might be helping you see the screen, to the camera on your phone, lenses are everywhere. They're these incredible pieces of tech we use every single day. But have you ever stopped to think about how they actually work? Well, it is a fascinating story of physics, and today we're going to bend some light and figure it all out. I mean, really think about it. How could something so simple, a piece of transparent, curved material, have the power to magnify tiny worlds, correct our vision, or even capture a star trillions of miles away? It feels like it should be magic, right? But nope, it's pure, elegant science. You can literally try this at home right now. Go grab a glass, draw an arrow on some paper, and look at it through the empty glass. Okay, not much happening. But now, fill that glass with water. Whoa. The arrow flips completely upside down. That little bit of visual trickery is happening because light is bending as it passes from the air, through the glass, through the water, and finally to your eye. And that simple effect is the key to understanding everything else we're going to talk about. So, here's our roadmap. We're going to start with the absolute basics, how a single curved surface bends light. Then, we'll build that up into a proper lens. After that, we'll learn how to predict the images it makes, uncover the math that powers it all, and then we'll finish up with a really surprising twist. Okay, first things first. Before we can even get to a lens, which has two sides, we need to get a handle on what light does when it hits just one curved surface. All right, to talk about this stuff, we need to know the lingo. Think of the principal axis as the main highway that runs right through the middle of our setup. The pole is the exact point where that highway hits our curved surface. And the center of curvature, well, that's the center of the giant imaginary ball that our curved surface was sliced from. These are our key landmarks. And here is the most fundamental rule in the book. When light travels from something thin, like air, into something thicker, like glass, it slows down. And when it slows down, it bends. It always bends towards an imaginary line called the normal. Then, when it goes from the dense glass back out into the rarer air, it speeds up and bends away from the normal. That change in speed and direction, that's refraction, and it's everything. So what happens if a whole bunch of parallel light rays, all traveling along our highway, hit this curved surface? Well, each one of them follows that bending rule. And something amazing happens. They all get directed to cross over at one single precise spot on the principal axis. And we call that special spot the focal point. It's like the ultimate destination for all that parallel light. So we've figured out the rules for one surface. Now let's see what happens when we combine two of them and build an actual lens. So what really is a lens? It's just a piece of transparent material, like glass, with at least one curved side, but usually two. So light comes in, bends at that first surface, travels through the glass, and then bends again as it comes out the other side. It gets a double whammy of refraction. And this double bending action basically creates two main families of lenses. You've got your convex lens, which is fat in the middle. It pulls light rays together, it converges them. Then you have the concave lens, which is skinny in the middle. It spreads light rays apart, it diverges them. And honestly, pretty much every simple lens is just doing one of those two things, bringing light together or spreading it out. All right, so if lenses can organize light like that, it means they can create images. And the best part, it's not random. We can actually predict exactly where an image will form and what it will look like using just a couple of simple, unbreakable rules. And here they are. These are like the 3 laws of motion for light through a lens. Rule 1. Any ray coming in parallel to that main highway has to go through the focal point on the other side. Rule 2. Any ray that goes right through the dead center of the lens just keeps going straight, no bending at all. And rule 3, if a ray goes through the focal point first, it has to come out traveling perfectly parallel. That's it. With just 2 of those, we can find any image. Let's put it to the test. Say we put an object, like an arrow, pretty far away from a convex lens. Okay, let's trace the rays. One ray from the tip travels parallel, and then bam, bends through the focus. Another ray goes straight through the center. Where those 2 lines cross, that's where the tip of our new image is. And look what we get. The image is smaller, it's upside down, and it's real, which means we could actually project it onto a screen if we wanted to. And this is where it gets so cool. Look at this pattern. As we slide the object closer and closer to the lens, watch the image. It moves farther away and gets bigger and bigger and bigger.
But then, something crazy happens when you move the object inside the focal point. The whole game changes. The image suddenly flips upright, it gets magnified, and now it's virtual. That means you can't project it anymore. You can only see it by looking through the lens. That's a magnifying glass.
Okay, so drawing those diagrams is a great way to see what's going on. But what if there was a cheat code? A single, elegant line of math that could predict that entire table without us having to draw a thing? Well, there is. It's called the lens formula.
This little equation is the mathematical engine behind everything we've just seen. It perfectly connects the object's distance, which we call u, the image's distance, v, and the lens's own special focal length, f. If you know any two of those, you can always find the third. It's a perfect predictor.
Now, there's one little catch to using this powerful formula. We have to follow a strict set of rules about what's positive and what's negative. It's called the sign convention. You can think of it like a map. The lens is at the origin, and this tells us if distances are to the left or right, or if heights are up or down. You have to follow these rules, because they're what allow the math to tell you if an image is real or virtual, upright or upside down. It's absolutely crucial.
Okay, for our final piece of the puzzle, let's challenge something we've kind of taken for granted. We've been talking about the focal length f as if it's this fixed, unchangeable property of a lens. But is it? Think about it. What would happen if you took your magnifying glass and tried to use it at the bottom of a swimming pool? Would it work just as well? Does the stuff around the lens make any difference at all?
And the answer is a huge, surprising no. A lens is not the same everywhere. When you take a standard glass lens and put it in water, its focal length actually gets longer. And a longer focal length means a weaker, less powerful lens. The environment totally changes the game.
The reason why is all explained by this, the lens maker's formula. Now, don't get hung up on all the symbols. Just focus on that little n in the parentheses. That n is the refractive index. And here's the key. It's the refractive index of the lens material relative to whatever it's sitting in. The difference in bendiness between glass and air is huge, so you get a short, powerful focal length. But the difference between glass and water, it's much smaller, so you get less bending and a longer, weaker focal length.
And this idea leads to some seriously wild, mind-bending results. Get this, an air bubble in water. It's shaped like a convex lens, right? It's thicker in the middle. But because the water around it is denser than the air inside it, everything gets flipped on its head. Light bends the wrong way, and that convex shape actually acts like a diverging, concave lens, spreading light out. So I'll leave you with that little puzzle to chew on. Based on everything we've just learned, especially about that all-important relationship between a lens and its surroundings, why exactly does that convex-shaped bubble of air and water act like a diverging lens? It's the perfect way to test your new understanding of how we see the world. Thanks for tuning in.